تهیه کننده Dr. Nima Mahdian. Producer Dr. Nima Mahdian. Hey everyone, and welcome. Let's just jump straight into it. Today we're undertaking a deep, focused exploration into the exact foundation of how our modern world maintains order in the middle of absolute chaos. This explainer is all about advanced control loops, the true bedrock of classical controllers. If you've ever wondered how a rocket manages to stay perfectly on its trajectory while ripping through turbulent atmosphere, or how a massive industrial plant perfectly balances hundreds of volatile variables all at the exact same time, well, you're definitely in the right place. So the overarching journey we're going on today is this continuous, basically unbreakable cycle. We start at the controller, move into the planter process, down to the sensor, and then loop right back around. And this isn't just theory, right? This is the active control loop. It's literally how we bridge the gap between the perfectly predictable world of whiteboard math and the messy, chaotic reality of achieving actual physical stability in the real world. Here's a quick look at our agenda for this explainer. First, the core objective. Second, the open loop problem. Third, enter the feedback loop. Fourth, the mathematics of control. Fifth, the 3 superpowers. And finally, number 6, the cost of autonomy. All right, section 1, the core objective. Feedback systems are basically the invisible hand of modern industry. The principles we're talking about aren't just abstract math exercises stuck in a textbook somewhere. They're the vital, inseparable core of how things actually get made and done. Whether we're talking about massive turbines generating power, the crazy complex piping and chemical processing, the pinpoint precision you absolutely need for aerospace rocket launches, or even automated assembly lines pumping out food, these control principles are the common denominator keeping it all running. Now, the core objective boils down to 3 crucial variables. We have R, which is our reference, or what we actually want to happen. Then there's Y, the actual output, where the system physically is right now. And the space between them, that's E, the error. The singular, relentless goal of any control system is to completely obliterate that difference. It calculates the error and just fights to push Y directly on top of R. That's the whole game. Moving on to section 2, the open loop problem. So let's look at paradigm 1, the open loop system. I like to call this execution without observation. Imagine a blindfolded archer. Sure, they can calculate the wind and distance perfectly beforehand, but once that arrow leaves the bow, 0 course correction. If a gust of wind hits, they're gonna miss. This is exactly how everyday devices work. Think about your toaster. It pops the bread out based on a rigid timer. It's completely blind to whether your toast is perfectly golden brown or literally catching on fire. Or a traffic light. It changes colors on a set cycle, totally oblivious to whether the intersection is completely empty or backed up for 5 miles. And that brings us to the real vulnerability here. Imagine we have our blind command sending out effort to run a process, but suddenly, boom, an external disturbance, let's call it D, strikes the system like a lightning bolt. Because an open loop system doesn't bother to observe its own output, that external disturbance silently and violently corrupts everything. The controller is completely ignorant. It just keeps sending the original command, blissfully unaware that the whole system is actively failing. Okay, section 3. Enter the feedback loop. Welcome to paradigm 2, the closed loop, or feedback system. This is the real game changer because we are finally introducing self-awareness. Unlike our blindfolded archer, a feedback system acts way more like a modern guided missile. By continuously measuring what it's outputting and feeding that info right back to the start, the system gains this incredible ability to dynamically adapt to chaos. It doesn't just cross its fingers and hope to hit the target. It constantly evaluates the environment and makes rapid course corrections on the fly. The secret sauce here is the return path. We add a sensor that translates physical reality back into a usable signal. And the engine powering all of this is the summing junction. The system now operates entirely on discrepancy. It mathematically subtracts reality, our measured output Y, from our expectation R, and that creates our error signal E. From that exact moment on, the controller has one sole purpose in life: drive that error signal to absolute 0, no matter what it takes. Let's do a really quick diagnostic comparison to recap. Open loop, no measurement, and it totally fails when external disturbances hit. But on the plus side, it's cheap to build and inherently stable by default. Now the closed loop, it actively compensates and neutralizes chaos using continuous sensor measurement. But of course, that comes at a cost. It's highly complex, requires expensive hardware, and introduces a brand new risk. If you design it poorly, it can actually become violently unstable. Which perfectly leads us into Section 4, the mathematics of control. Before we dive into the heavy equations, I want you to anchor yourself in actual physical reality for a second. Think about a gear in a machine. Over time, the physical parameters of literally any system are going to change. Motors run hot, friction kicks in, environments shift, and a pristine, shiny piece of metal eventually turns into a rusty, degraded, worn-out part. If our original math relied on that pristine gear, how on earth do we guarantee the system still works flawlessly decades later when it's all rusted out? Well, here is where the math gets absolutely beautiful. In an open loop, you're directly vulnerable. If your physical process degrades by 10%, your final output degrades by exactly 10%. There is zero protection. But check out the closed loop equation. That return loop actually creates a mathematical denominator, 1 plus d of s times g of s. This is what we call the feedback shield. If we design the controller, d, so that its gain is massively large, that 1 in the denominator basically becomes negligible. So the d and g on the top and bottom effectively cancel each other out. The math magically simplifies, meaning our output is virtually equal to our original reference. The system literally ignores its own physical degradation. How cool is that? All right, Section 5, the 3 superpowers. Let's see what this math actually buys us. Superpower number 1, disturbance rejection. Remember that lightning bolt of a disturbance from the open loop system? Well, in a feedback system, when a massive wave of external chaos slams into the process, the sensor instantly detects the spike in the error. This forces the controller to immediately fire back with an equal and opposite response, effectively neutralizing the chaos before it even has a chance to ruin the final output. Superpower number 2 is handling model uncertainty. Look, as engineers, our mathematical models of a motor or a chemical reaction, they're always just rough approximations. They are never 100% perfect. But feedback acts as this incredible engineering safety net. It totally forgives our imperfect math, allowing the system to function with extreme precision in the real physical world, even if our foundational models were just kind of ballpark estimates. And superpower number 3, taming process instability. Some physical processes are fundamentally unstable by their very nature. They will fail catastrophically if you try to use an open-loop control. Think about trying to balance a tall rod on the tip of your finger. It constantly wants to tip over and fall, right? A well-designed feedback loop processes that falling motion so incredibly fast that it generates a counter-movement, literally forcing mathematical stability onto mechanics that are inherently chaotic and unstable. Finally, Section 6, the cost of autonomy. Of course, in engineering, superpowers always come at a price. It's a strict architectural trade-off. On one side of the scale, yes, we gain incredible capability, intelligent adaptation, and error neutralization. But on the other side, we're looking at massively increased design complexity and much higher manufacturing costs, simply because you suddenly need these incredibly precise, expensive sensors. And then there's the paradoxical risk. If you tune a feedback loop poorly, you can induce a delay that causes the system to overcorrect. You can actually introduce severe violent instability into a system that was perfectly stable to begin with. So it really all comes down to this. The ultimate engineering challenge is designing the brain, the DS controller block. What exact mathematical operations should this brain perform on the error signal to generate the absolutely perfect command? This right here is the complete architecture of autonomy. It's exactly how classical control takes blind execution and transforms it into intelligent adaptation. By mastering that DS block, engineers can harness the mathematics of error and the sheer power of the return loop to actually achieve stability in a totally unpredictable world. And that is the foundation of classical controllers in a nutshell. To wrap up this explainer, I want to leave you with a final thought to really reflect on, not just for engineering, but honestly for any complex process you manage in life. Look closely at the systems around you. In a world of ever-increasing chaos, is your system rigidly designed to just blindly execute until it completely fails? Or is it designed with the critical feedback loops necessary to adapt, correct, and survive? Something to think about. Thanks so much for learning with me on this explainer, and remember to keep questioning the systems around you.